Okay, so last time out, we talked about eigenvalues and eigenvectors. And remember that eigenvectors were essentially just special vectors associated with square matrices, where we can multiply a matrix by that vector, and we just get some scalar multiple of that vector. And this turns out to be really important when we're trying to solve the long-term dynamics of various dynamical systems. And we're going to be talking about some of those today in terms of population models. These are the really simple linear population models, and they are essentially an extension of what you would have looked at in one dimension previously in Math 154. Who remembers looking at these in Math 154? Yeah, so really simple population models. And really, the key thing is we have some equation, Pn plus 1 is equal to A times by Pn, where Pn is just our vector of our population in year or generation n. A is telling us something about the births and deaths, maybe migration or some other processes. And then Pn plus 1 is what we get in the next year. Okay, so we can iterate this over and over and over and over again. And so really what we care about is the limit as n tends to infinity. So when n gets really, really large, of our matrix A to the power of n times by our initial population. Okay, so this is what we care about trying to work out. And obviously, we don't want to just have to keep multiplying our population by this matrix over and over again by hand or by computer, because that could take a really long time. It'd be great if we could just look at some simple properties of that matrix to tell us what is going on in the long term. And that's what our stuff about eigenvalues and eigenvectors, that's where that comes in. Okay, so if we just go back to our very simple scalar population model that you would have looked at before, the long-term solution to this, well, if we look at our population in year n, so imagine that P0 here is just going to be our initial population. Say it's just the size of the human population in a particular year. We have some births and we have some deaths, and this ultimately gives us a growth rate, and we can find our population size in year n by taking our growth rate to the power of n and times that by our initial population. Okay, so this just gives us exponential growth or exponential decay. So really all that matters here, if I zoom in, we care about this lambda n. Okay, what is lambda? That will tell us something about whether this population is growing or decaying. So it doesn't matter really what our initial population is as long as it's not 0. We care about what's going on with lambda. And it's essentially the same thing if we have more complicated populations. So now rather than just having a homogeneous population, we're going to have, say, an age-structured population. So we want to think about individuals in those different age classes. So they might be juveniles. You could do them for every single year group. They might be juveniles, they might be adults, they might be elderly. And each of those classes might have different death rates. They might have different contributions to birth rates and so on. So we can split our populations up into these different classes. And then we can form a linear system based on those models. Okay, and this is ultimately going to lead us to something called a Leslie matrix. So we went through this example in the pre-lecture material. Can I just have a quick show of hands who actually watched that? Fantastic, thank you. So given a word problem like this, where we have some information about how individuals are aging, how often they die, or how likely they are to die, we can turn this into a linear system like we have below. We'll go through an example of this today. And then we can just write that then as a Leslie matrix by taking those coefficients and putting them into our matrix. And then we can use that either to project forwards, or if we can work out the eigenvalues and the eigenvectors, figure out what's happening in the long term. So where does this all come from? Well, there are a couple of slides about this. I'm not going to go into this in too much detail here in terms of the underlying mathematics. What I really want you to focus on is the idea of a dominant eigenvalue in this system. Okay, so we can write down an equation that tells us the general solution. And so that's what we mean by this thing here at the bottom, that in year n plus 1, the population we can write as some constant C1, so this is just a scalar, times by our first eigenvalue lambda 1 to the power of n times by its associated eigenvector u1. Add all of the other combinations of eigenvalues and eigenvectors. Okay, so we can write our solution in this form. And then let's think about if lambda 1 is our biggest eigenvalue, So it's dominant in this system. And that means that lambda1 is here, lambda1 is greater than the absolute value of all of our other eigenvalues. Well, if this is our solution here, we can take out a factor of lambda1 to the power of n, put it out the front. That's all that's going on this next line here. So we put it out the front. That gets rid of it in this first term here. And then we essentially have to divide through all of the other terms here. And since lambda1 is bigger than lambda2, lambda3, lambda4, all the way up to lambda m, that means that when we take any of these things here, any of these to the power of n, as n gets really, really large, they're going to get really, really small. And so all of these things in this bracket here, I'm running out of things to color in here. All of those things on that right-hand side, they all are going to get really, really small compared to the thing on the left-hand side. So that means that our long-term solution essentially tends towards just this very simple thing here, which is determined by a constant. That constant is determined by our initial conditions. So we're not going to worry too much about this now. Times by our dominant eigenvalue to the power of n, times by our dominant eigenvector. So the eigenvector is going to tell us about the distribution of those different classes. And the eigenvalue is going to be telling us whether the population is growing or shrinking or staying constant, or going to tend towards constant. So the other thing we can do with the eigenvector, like I say, is it tells us about the proportions. Remember that our eigenvectors are only unique up to non-zero scalar multiplication. Okay, so remember there's an infinite number of different eigenvectors that you could pick, but there's a special way in which we can arrange them for our population models. If we divide through by the sum of the terms in that eigenvector, then we can write down this as the proportion that will be in each class in the long term. Okay, so there's a special way we can do this. So in this case here, suppose our eigenvector was 3, 1. Well, from that tells me that the long-term ratio is going to be 3 times more in this, whatever this first class is compared to the second class. If we add these up, we get 4 and divide through. And we can also see in the long term, we're going to have 3/4 of the population in this first class and 1/4 in the second class. Okay, so this is just a different way of writing the eigenvector that tells us something about those long-term proportions. Can everyone hear me at the back? I realize I didn't turn the mic on. Yeah. Okay, great. Okay, that was a quick summary of everything that was in the pre-lecture material. Before we move on to problems today, does anyone have any questions? Nope. Okay, let's go through some problems. Okay, so I talked about Leslie matrices. Leslie matrices are just a particular type of matrix that we use in our population models, okay? So they have a particular form, and some things we can think of as being making sense as a Leslie matrix, and some things won't. So we're just going to run through now what this Leslie matrix looks like, and what we can learn from the different quantities within it, okay? So first of all, if this is a Leslie matrix here, L, can you tell me how many age categories there are? Altogether? 3, okay. So it's a 3 by 3 matrix, so there are 3 age classes. Okay, how many offspring do the adults produce on average? So I'm going to assume that this first row and column is going to be, say, juveniles. Then I'm going to call these sub-adults. So you can think of those as being like adolescents, and then adults in the third row and third column. So how many offspring do the adults produce on average? Okay, how do we work this out? Well, new things coming into the juvenile class are going to be determined by this first column here. Right? Sorry, first row. And the adults are the third row, third columns. That means that we care about this term here, this 2.1. And that is telling me that every adult on average is producing 2.1 juveniles per year. So 2.1. That's this term here. So there's a biological interpretation for every single one of these elements in this matrix. In that case, what does L21 signify? So this is L21 here, this is 0.3. So remember the indexing, the first, if this is Lij, the I is the row and the J is the column. So L21 is the second row, first column. So what does L21 signify? Exactly, yeah. So this here is going to be essentially juveniles aging into the next category, so into sub-adults. Okay, how about these zero terms here? So why are L31 and L230? Yep.
There's no juveniles there, but there's no
Exactly, yeah. So this, I'll do it in a different color here. This term here, if we were to multiply this out, imagine we've got I'm going to call this JN, SN, and AN. If we were to multiply this out, this would be the contribution of the juveniles to the adult class. So in other words, what the flow from juveniles to adults. But as Rowan just said here, we can't just flow from juveniles to adults. We have to go through the sub-adults class. They have to age through that, that intermediate class. So this doesn't make sense for them to jump past the sub-adults class. Okay, so that's why that's 0. And this other one here, well, that would be the contribution from the adult class to the sub-adult class. So they can't age backwards, right? So that wouldn't make biological sense for that to happen. Okay, so I'm not going to write that out, but it's on the solutions in case you want to, in case you can get all of that. Okay, what proportion of adults survive each year? Someone else. There aren't that many terms left here. So any idea? 0.6, I don't know who said that. Great, thanks very much. Okay, so 0.6, so it's just this proportion here that is telling us how many adults are staying adults. Okay, so we're seeing that 40% of them are dying, so we can say that 60% survive. Okay. So let's go through a few more examples to see what things make sense to be Leslie matrices and what don't make sense to be Leslie matrices. Okay, so here we've got some examples. How about example A? Are there any reasons as to, well, can you tell me first of all if it's a Leslie matrix or not? So hands up who thinks that A is a Leslie matrix. Hands up who think it isn't. Okay, can someone with their hand up now tell me why it isn't? Yeah. Okay, yeah, so this term here, that's not equal to 0, okay? So that's telling me that someone's jumping, or the proportion of the population is jumping from the first class to the third class. We can also see as well that these things here, sum is greater than 1. So this is also a problem actually, right? Because what this is saying is that this term here, the 1 in the first row, is saying that 100% of the juveniles stay juveniles in the next year. But then 90% of them also age. So we've suddenly got 190% of the juveniles. So also think about what it means for some of these terms to add up. In this case, the sum of these things here is greater than 1. Okay, how about B? Could this be a Leslie matrix? Yes, hands up. No, hands up. Not sure, hands up. Don't care, hands up. This could be one. I put it across there. This could be one. So here, for example, this sums to 1. It doesn't have to sum to 1 because individuals could be dying, but this is saying 10% of our juveniles stay juveniles, 90% age. That's fine. That's not going over 100%. We haven't got anything else in here that says that it could be a problem. Okay. C, can C be a Leslie matrix? Hands up for yes. Hands up for no. Okay, why can't it be a Leslie matrix? It's not square, okay? So because we need to think about contributions between each of these different classes, so that's individuals that are being born, individuals that are dying, and so on, this needs to be a square matrix to be a Leslie matrix. This is not square, so it can't be a Leslie matrix. D, hands up who thinks this could be a Leslie matrix? Who thinks it isn't? Okay, why isn't it? Great. So this is negative. We can't have a negative number here because we're going to end up potentially with a negative population. So this is not. E, could this be a Leslie matrix? Hands up if yes. Hands up if no. The answer is yes, this could be. Note here, in this case, we've got a 0 here, so this basically means that all adults die. Okay, so this would be a case where we've got a, this is common in, say, insect populations where they don't live for very long, they reproduce and then they die. Okay, so they don't survive necessarily year on year, but say things like eggs will overwinter. F, could this be a Leslie matrix? Hands up for yes. Hands up for no. There's no problem with this one. This could be a Leslie matrix as well. Okay. So we've definitely got a few Leslie matrices here. If we focus on, let's just focus on B and F. We know that these can both be Leslie matrices. Let's think about, first of all, how many age categories there are. So let's do everything for B first. So how many age categories are there in B? 2. Okay, it's a 2 by 2 matrix, so there are 2 age categories. What proportion of each category survives to the next stage? So we've only got one category that can survive to the next stage. So what proportion survives to the next stage in B? 0.9. Yep, so it's this thing here. So elements below the main diagonal are going to tell us about aging. Okay. Elements above the main diagonal tell us about, births or things that are going back in time, right? So we definitely don't want things to be de-aging, but things below the main diagonal will tell us about what is aging, okay? So in this case, we've got 0.9, so I'll just write this as 90%, so that's clear. So 90% survive to the next stage. And how many newborns are produced by each category? So how many newborns are produced by the adults here? On average per year? 1, so we'll take 1. So yeah, this is just this one here. So remember, elements above the main diagonal are going to tell us about births. So 1 per adult. These models are always on averages, right? So we're assuming that our population is deterministic, it's large, and it behaves well. We're not accounting for random effects in these things or variation within that population, really. So we're just going to say 1 per adult on average. Okay, let's go through matrix F. So how many age categories in matrix F? 3. Okay, so again, this is a 3 by 3 matrix. So the size of our matrix will tell us how many age classes there are. Okay, so because there are 3 age classes, for the next part, we're going to have 2 aging events, right? So we've got to go from class 1 to class 2 to class 3. So what proportion of each of the first class survives to the second class? 90%? Yeah. So again, this is 90%. Let's call them juveniles, just subadults. How about from subadults to adults? Someone else? Anyone else? Yeah. 20%, great. So again, we're thinking about elements below the main diagonal. In this case, this is 20% of our subadults are surviving to adults. Okay, so 20% from subadults to adults. How many newborns produced by each category? Get rid of these. Okay, so how many newborns are produced by subadults? Sorry? 0.4, great. So again, we're going above the main diagonal here. So 0.4. So one of the reasons we might want to split these populations into different classes is because they have different fertility rates. So for example, males that are younger may be less competitive than males that are older, and therefore they produce on average fewer offspring. So 0.4 per year on average. So I'll put this per year. Again, on average for sub-adults. And then for adults, how many offspring on average are adults producing? 4. Yeah, so that's this one up here. So remember our births, they are going to be all, when I say it's above the main diagonal, it's everything along the top row. Okay, so that's what we care about. It's that 4 there. So that's 4 per year on average for adults. Okay. So let's think now about building a Leslie matrix. So there was an example of this in the pre-lecture material. And I'll help you out for the start of this one. We've got here a population of bears, and we're going to divide them into cubs, adults, and elderly. So I'm just going to define this vector here as Cn as my cubs in year n, An as my adults, and for En as my elderly bears in year n. So I haven't written this out in full here just for the sake of time, but whenever you are starting a problem like this, you should define what each of your variables are. Don't just assume that I know that Cn is cubs in year n, so you should write out, cubs in year n is Cn, adults in year n is An, elderly in year n is En. Okay, now we want to write down a Leslie matrix. So what's going to be the size of this Leslie matrix? 3 by 3. Okay, so we're going to have 3 rows, 3 columns because we've got 3 age classes. And then how do we work this out? Well, we've got all these different pieces of information here. So I'll go through this first one here. So we're told that get rid of that. We're told that a third of the cubs become adults and 10% are killed. Okay, so always think about we're starting with 100% of the population, and then we're going to be taking things away. So we're going to be thinking about individuals going from the first class into the second class. So let's think about individuals who are being removed from this first class here. So we're going to start off with 100%. So we've got a proportion of 1 here. We're told that a third of them are going to be aging. So we're going to subtract a third. And 10% of them die. So a 10th die. Now we need to fill in some of the other ones as well, potentially. So here, because we're told that a third of them age, we need to fill in aging as well. So we put a third down here. So the third are going from that first class into that second class. The 10th we don't do anything with because they're just dying, so they're just being removed. Okay, so we don't have to put that 10th anywhere. Let's see, what else are we told? Adult bears produce on average, do it in a different color. They produce on average 2.1 cubs. Okay, so remember our first row is going to tell us what's going on with births. So adult bears produce on average 2.1 cubs. So this second element here on the first row is going to be 2.1. Let's move it over a little bit so it's a bit clearer. It's 2.1. And elderly bears, that's our third age class, they on average produce 0.6 cubs. So this one here is 0.6. Okay. Have a go at filling in the rest of the entries. I'll walk around and you can ask me any questions you might have. Okay. Okay, there's quite a few questions about this. So I appreciate I can't see everyone in the space for a few minutes, so I'll go through a few of the things that people asked. And if you still have questions, obviously you can ask me after this. I have office hours as well, straight after class in the ACW. as of last week, if you can go to the ACW and ask me questions at office hours, please do, rather than coming at the end. People come and ask me questions at the end if you can't go to office hours. In addition to that, remember, you can also go to the ACW to speak to TAs if you need someone to work through this in a bit more detail. Okay, so quite a few people asked me for clarification on what these different rows and columns mean for our matrix. I'm just going to write in some, I'm just going to put in some holders here, okay? These different things that will end up in those elements. What do each of these things mean? So this main diagonal here, going from top left to bottom right, that is essentially everything that is staying in that age category. Okay, so think about when we multiply this out by our vector. So this vector is going to be on this side here. So what do we have? Well, if we think about the contributions into the next year, this element here is going to get multiplied by this Cn here. So this is going to be Cn's that are contributing to Cn plus 1. Okay, so those are going to be things that survive into the next year. This element here in the middle, so second row, second column, is going to get multiplied by our An. So that's going to be An, adults in year N, that are contributing to adults in year An plus 1. So again, that's things that are surviving from one year to the next and staying as adults. And then this third one here is similarly going to be everything in our elderly class that is contributing to the elderly class in the next year. So again, things that are surviving from one year to the next as elderly. So there's no aging going on in any of those categories, okay? What else can we tell from this? So everything below this main diagonal is going to be aging. Okay, so this is things that are going from, say, Cn to An, An to En. And in fact, unless we're doing a very weird example where we would have something skipping a class, which we're not going to do, we're not going to be thinking about things like that. This thing here is going to be aging into the next class. So the diagonal that's directly below our main diagonal are going to be things that are aging into the next class. And then this thing here should be 0. Anything below that, we could be doing a 4 by 4, 5 by 5, and so on, in which case we would have a triangle down here. This would be everything that's skipping classes, okay? So we don't want that, so we're going to be setting those things to 0. Okay, what else do we have in this? Well, what about above that main diagonal? So above that main diagonal, the remainder of this first row, that's going to be births. Again, think about what happens when we multiply out by this matrix. This is going to be, if I do it one by one, this element here is going to get multiplied by An, and that's going to be our contribution to Cn plus 1. So this is adults producing cubs in the next year. Likewise, if I think about this element here, that's going to get multiplied by En to give us something in Cn plus 1. So in both of these cases, we have births. So that's the biological interpretation here, that the rest of that first row above that main diagonal is going to be births. And then the last thing we have that I haven't colored in yet is going to be this element here. And the interpretation of that element would be something that's going from the third class into the second class. So the elderly cubs becoming adult cubs. So this is de-aging. Okay, and unless we're doing like a sci-fi example where we're imagining that there is de-aging, we have no Benjamin Buttons here, this is going to be 0 in all of our biologically plausible examples, okay? So these are the different biological interpretations of the elements within these matrices, okay? So just to recap that again, the things on the main diagonal are staying in that age class, so things surviving in that age class, they're not dying, they're not aging. Things that are in pink here are things that are aging. Green is aging but skipping a class, so biologically that's implausible, we're going to set those to 0. Things in blue are births from each of the different classes, and then that brown one is going to be de-aging. So again, biologically implausible, so that will be 0. Of course, this is for a 3 by 3. This could be for any number of age classes, so some of these, the green and the brown thing could be triangles, okay? Right, so I appreciate that there probably are quite a few questions on that. And some of these, we won't have time to go through all of these today. So does anyone have any burning questions of clarification about what I just said there? Is that itching your hair or fixing your hair? Okay. Let's go through what these actually are in this example then. So the next row we're told here, so row 2, a tenth of the adults mature to become elderly and 5% die. Okay. So what does that mean? Well, just like we did with the juveniles in that first element, so first row, first column, we're going to do a similar thing in the second row, second column. We're going to start with all of our adults. So we've got a proportion of 1. We're going to subtract a tenth of them, which are maturing, and 5% die. So that's 1/20. And then we're not going to put anything in for the ones that die, but we need to account for the ones that are aging. So just as this third here goes down to the next row, that tenth here goes down to the next row here. So these are adults that are becoming elderly. And to complete this, let's do the last row as well. So we're told here that 25% of the elderly bears die. This is our final age category, so there's no aging here. Okay, so all we have is our initial population, so a proportion of 1, minus those that die, 25% or a quarter. And the 2 elements I have left, the one in the bottom left, remember that's aging but skipping classes, so that's biologically implausible at 0, and then the one on the second row, third column, is individuals who are de-aging. Again, biologically implausible, so that's going to be 0. Okay, so that's how we solve this, or how we write down a word problem into a Leslie matrix. Okay, we've only got about 9 minutes left, so I will work through a little bit of this problem with you guys, okay? Again, maybe go through this in your own time with the full solutions. Here we've got a 2-category system. So we've got some young individuals and old individuals, so young and adults. We've got some details about how they mature. I'm going to refer to these adults as AN in year N, and the young as YN. My population vector in year N, I'm just going to define as YN AN, so each of the classes that we have. My Leslie matrix, well, what have we got? So we're going to start off with a population of 1 for our young. We're told that a third mature and a third die. So we're going to do 1 minus the third is going to be that first element. A third mature, so I write that on the second row. Adults, we're told, produce 1.1 young on average. So this is going to be a 1.1 in this top right. And half of them die. So we're going to have 1 minus a half in this bottom row. So writing this out as decimals, we have 0.33, 1.1, 0.33, recurring obviously, 0.5. Okay, so the second part I'll leave for you guys to do. But if we're told an initial population here, so we've initially got in year 0, so Y0, we've got 120 young, and our AN, our A0, is going to be 100 adults. How do we work out what's going on in years 2 and 3? Actually, these are called year 1, so rather than zeros, I'm going to put those as 1s. So Y1 and A1. You want to work out what's Y2 and A2, and what's Y3 and A3. Well, remember that our population in year N plus 1 is going to be L. So our matrix, Leslie matrix L, to the power of N times by what was in Pn. So have a go at doing that one in your own time and work out approximately how many individuals we have. Remember also that we're not going to have half or fractions of individuals here, so you'll want to round them as well. Okay, that'll leave as an exercise because that's just calculation. I talked at the start about eigenvalues and eigenvectors and why they're important. So let's think about it in the context of this example here. So we can work out our eigenvalues. Remember, to work out our eigenvalues, you want to work out the determinant of our matrix minus lambda, which is going to be our set of eigenvalues, times by I, which is our identity matrix. And we're going to set that equal to 0 because this is our characteristic equation. Again, this is a calculation thing, so I'm going to skip over this here. Again, work through this in your own time. If we do this, we get two eigenvalues. One of them is approximately 1.03, and the other one is about minus 0.194. So what can I tell from this? Well, I can tell immediately that because lambda 1 is greater than the absolute value of lambda 2, that this is going to be my dominant eigenvalue of the system. So in the long term, this is going to dominate the population. I can also write down an eigenvector associated with this. So we went through how to write down eigenvectors before. If I write down L minus lambda 1, so my dominant eigenvector here, and my eigenvalue times by its associated eigenvector, which I'll just call x1 here, we're going to have minus 0.69, 1.1, 0.33, minus 0.53, I think I've got that written down as. So that's just my L minus lambda 1, with lambda 1 as 1.03. So lambda 1 times by I. This can be times by my eigenvector, and this is going to be equal to 0. So we can use that trick that we talked about the other day to work out what is x by taking these elements here, switching them and changing the sign of one of them. So here, if I put the 1.1 up top and 0.69 at the bottom, I've now got an eigenvector. So this eigenvector is only unique up to scalar multiplication, non-zero scalar multiplication. So if I add all the terms up in this eigenvector and divide through by them, then I'm going to end up with something that sums to 1. So I'm going to write this now as 0.61, 0.39. And the way I got that was summing up these elements in X and dividing through by them. When you do that, you'll get a vector like this. So again, I appreciate I'm going through the calculations here and not really talking about them in too much detail, skipping over them. I just want to focus on the process of how we get to this answer. If you want to work through the calculations in your own time, please do. So why have I done all of this? Okay, so I've got an eigenvalue, a dominant eigenvalue, lambda 1, which is greater than 1. I've got an associated eigenvector. What does this tell me? So if I want to know the long-term behavior of the system, I need to think about what's going on with my dominant eigenvalue and the eigenvector, okay? So just hold on a minute, guys. You've got 3 minutes left, okay? So you've got your population in your n plus 1. It's going to be L to the n times P0. And this is going to tend towards some constant times by our dominant eigenvalue, lambda 1, times by our dominant eigenvector x1, okay, as n gets large. So what do we know about this? Well, lambda 1 was 1.03. So we're going to be taking 1.03 to the power of n. So this is greater than 1. So when we take this to the power of n, this means that it's going to be getting larger and larger and larger. So this tells us that the population is going to be growing exponentially. We also looked at that eigenvector, remember, from above. In the long term, our population is going to tend towards the proportions determined by that eigenvector. So we know that the population is going to be growing, but in the long term, we're going to have approximately 61% in the first age class, the young, and 39% as adults. And we get that by looking at this eigenvector here. So I don't have to multiply this out loads and loads and loads of times to figure out what's going to happen in the long run. I can just look at my matrix, find my eigenvalues, find my eigenvectors, look at what is the dominant eigenvalue. I don't even need to find the other eigenvectors, in fact. I just need to find my eigenvalues, find the dominant one, find its associated eigenvector. The magnitude of this eigenvalue tells me if the population is growing or shrinking. So if this was less than 1, then it would be shrinking. And the eigenvector tells me the proportions. Okay, thanks, everyone. I've got office hours now. And if not, I'll see you on Monday.